Okay, so we're gonna pick up with section 2.4. This is more talking about prefixes and the beginning of the conversation on what we're going to call equalities, which is when we have two things that are equal to one another. So starting off with our prefixes, these are typically found in our metric system. Okay, and our prefixes are going to be placed in front of any unit, and that prefix will either increase or decrease the size of that unit by a factor of 10. So these are two examples of prefixes, milli and micro, and both of these prefixes will make a unit smaller. So if you have, for example, the unit gram and you put the lowercase m in front of it, it becomes milligram. And a milligram is smaller than a gram. And we'll look at how much smaller when we look at the table with the equalities inside of it. Okay, so your the table that's in your notes, there's two tables really in your notes, or it's one table that's been split into pieces. Um, the prefixes that go from peta up to kilo represent prefixes that will increase the size of the base unit that you start with. The base unit is going to be the unit without any prefixes attached to it. All right, so let's just write that down. And then when we add a prefix to a base unit, that's going to increase or decrease the size of our base unit. Just depends on what the prefix is. So for example, if our base unit is a meter and we put the kilo prefix in front of it, then it would be a kilometer. And a kilometer is going to be larger than a meter. So it's increased the size of that base unit. Um, Now, what you're seeing on these tables is the name of the prefix and the symbol that goes along with them. You have to pay attention with prefixes not only to the letter, but to whether the letter is capitalized or not. So you'll see here there's a prefix mega, and that prefix mega is given a capital M. And it's often confused with milli, but the prefix milli has a lowercase m. Okay, if we're sort of continuing on the table here. And these are going to be the most of the units that will decrease the size of your base unit instead of increase them. So you want to pay attention to both the the letter as well as the capitalization. Okay. And another prefix that you want to kind of watch out for is the micro prefix here. There's a slide on this later that we can look at, but you'll see that the symbol for the micro prefix, because we've already used our lowercase m, it's this like it looks like a scripty U. Okay. There's a fancy name for it, but it looks like a scripty, a script written U, like a cursive U. Um, but a lot of times people will use a different combination of letters for this instead because it's really easy to misread this symbol. And so the combination of lowercase m, lowercase c gets used for gets used to represent micro as well. Okay, but like I said, we'll see that in another slide. Um, so that's the name of our prefix. That's the symbol of our prefixes. The other thing I really want you to pay attention to is the scientific notation value of the prefixes, because these are going to contain the exponents that we're going to need in order to make our equalities. Okay. And so when you're making equalities, you're going to notice that some of the scientific notation values they have positive exponents, like this batch here. And then once you get to deci, the exponents turn negative. So 10 to the -1, -2, -3, -6, -9, -12, -15. When you are writing out equalities, the procedure that is going to be helpful for you to use when you're writing them out is going to be to equate one of your prefix values with this number of base units. Okay, whatever this number that's in your scientific notation, whatever that exponent is, 10 to the -2, 10 to the -6, 10 to the +15, this should represent the number of base units that you have that are equal to one of your prefix values, your prefix units. Okay, so I want you to, we're going to keep this in mind. I'm going to write out a few examples from the table just to show you what I'm talking about. It's easy for me to say that, but I don't think it's always easy to understand what it means. So let's write out from our table. We'll write out like 3 examples of prefixes, symbols, and then I'm going to skip the numerical value. I'm going to go to scientific notation. Because these are the 3 things that we really need to write out our equalities. So let's do we'll do a mega. We can do kilo. And then we can do milli. Okay, so capital M, lowercase k, which doesn't look very lowercase. I'll make it a little shorter. And then lowercase m. Okay, and then the scientific notation that you get right from that table, for mega, it's 10 to the +6. For kilo, it's 10 to the +3. And for milli, it's 10 to the -3. Okay, so that's the information from our table. What I want to do is practice making equalities from the values on our table. Okay. Now, if we go back up to the definitions that we wrote here, base unit and prefix. Base units are going to be any of the units that we use to describe those measurements that we're taking, that we've been practicing with. So types of base units. Things like gram, meter, second, liter, joule, if you're talking about energy. Let's see, I did mass, we did volume, we did that. But you get the idea, right? So like notice that all of these units, none of them have a prefix associated with them. So all of these would be considered base units. So let's say that we want to write out an equality that relates grams and megagrams. Okay. So grams and megagrams. To make this equality up, we're going to put a 1 in front of our prefix value. So we're going to say that 1 megagram, capital M, G, that's megagram. 1 megagram is going to be equal to 10 to the 6 grams. That's our equality. And from the equality, you can build your conversion factor. So the conversion factor that goes along with this well, there's 2 conversion factors that you can write from every equality, right? So the conversion factors that go along with this will be that 10 to the +6 grams are in every 1 megagram, or 1 megagram, 10 to the 6 grams. Okay. Let's do a similar setup, but we'll do kilometers and meters. Okay. We'll stick this one down here. Kilometers and meters. So we're going to put a 1 in front of our prefix value. So we're going to say that 1 kilometer equals whatever our exponent value is, our scientific notation value. That goes with our base unit. So 1 kilometer is 10 to the third meters, or 1 kilometer is 1,000 meters. Okay, let's say I wanted to do seconds and milliseconds. Okay, I'm going to put a 1 with my prefix. So 1 millisecond equals 10 to the negative 3 seconds, which is my base unit. And then from my equalities, I can make my conversions. There is more than one correct way to write out these conversions. For example, when people are relating the milli prefix to the base unit, it is very common for people to write that that in 1 second there are 1,000 milliseconds. And that's correct. There's nothing wrong with that. The pattern that I'm showing you here, where you keep the 1 with the prefix and you keep the exponent with your base unit, I'm showing you that so that you can apply that to every situation. So if you're ever not sure that you have a pattern to fall back on, and then you can use that to create your conversions if you're working with a unit that you might not be familiar with. Okay. So we're going to look through some of the equalities for the different types of measurements, and a lot of them are going to look familiar now because we just looked at this table. But we'll take a peek at them. All right, so the relationship of a prefix to a unit can be expressed by replacing the prefix with its numerical value. So what that means is that you can take a measurement and you can say that, yeah, the distance that I traveled was 1,000 meters, or you can say the distance I traveled is 1 kilometer. And both of those express the same distance. Okay, so that's the purpose of using these prefixes. So one thing we want to be able to do is figure out how our base units and our prefixes are related to each other. So what this question is asking us to do is kind of look back at that table of prefixes and figure out, what the match is here. I'll write these down and then we'll talk them out. So the blanks here are the prefix that would make the equality true. Okay. So there's 2 ways you could approach it. Like, you don't have to write out, like, I'm going to write things out a little more because I want to make sure that everyone understands. You can use your table that has your exponents on it to help you find the prefix here. If you find that it's easier to like match the exponents and find the prefix, then what you would need to do with numbers like in A and C is you need to rewrite these values so that they're in scientific notation so that you could look at the exponents, right? Another way to write 1,000 in scientific notation is to recognize that you'll be moving that decimal over 1, 2, 3. So this value is the same as 10 to the positive 3. Okay. And the exponent 10 to the positive 3, that goes along with the kilo prefix, right? 1 times 10 to the negative 3, the negative 3 prefix goes along with the negative 3 exponent rather goes along with the milli prefix. Okay. And then here we have 0.01. So if we want to write this in scientific notation form, we would move that decimal over 1, 2 places. So our exponent here would be -2. And the -2 prefix is centi. Okay. All right, let's take a look at some of these other. All right, so here are some common length equalities, right? 1 meter is equal to 100 centimeters. That's another way that we can think about the equality. Or we can follow that format that we discussed and we can say that 1 centimeter equals 10 to the -2 meters. These values, they mean the same thing. Okay. That's another thing that it takes a minute to understand, and like to understand when you're looking at things that look different, but they actually mean the same thing when you are looking at the mathematics of it. But this is one of the examples I was talking about where this is a perfectly acceptable way to write that equality if that's the way that you already know it. But if you have no real attachment to it, then that's fine. Then you can write it in the format that we've been discussing. Another common equality that you'll see in terms of distance or length is that for every 1 centimeter, there will be 10 millimeters in that 1 centimeter. That's how our standard metric rulers are broken up. When we measure volume, the type of unit that we're going to use depends on the quantity of the substance that we're measuring, right? Usually liquids. For liters, that means we're working with pretty large amounts of material. Usually when you're in like the health sciences field, the volumes that you're using are not going to be in quantities that are this large. So it's a lot more common to see things in terms of deciliters or milliliters. Okay. So if you take a liter and you divide it up into 10, each of those units is going to be a deciliter. There are 10 deciliters in 1 liter. And then for your milliliter, there's 1,000 of those milliliters in 1 liter. And then we have a very common unit, the cubic centimeter. This is especially in like the health field that the cubic centimeter you have to be familiar with. Okay, now there's a lot of equals things that are written down here, so I want to make sure that we understand that part. First of all, the cubic centimeter gets its name because when you take something that is like cube shaped, that's like square shaped, and you measure each side of that in centimeter units, and you do length times width times height, and each thing is measured in centimeters, the unit that you end up with is going to be centimeters cubed. And that's where the cubic centimeter unit is coming from. Now, the cubic centimeter unit is written out literally as the centimeter unit, but with the exponent of 3. Okay. Let's say that you have an actual cube that you're looking at. Oh boy, I'm gonna draw this out. Okay. So in a cube, you have it's kind of arbitrary what you're calling length and width and height. But let's say that this is our length, this is our width, and let's say that this is our height. All right. So now each of these I have to take a measurement of. I'm going to make this easy for myself. So I'm going to say that the length for our cube here is 1 centimeter. The height is 1 centimeter and the width is 1 centimeter. Okay, that's the cube that I'm measuring. When I go to find the volume of this, volume is length times width times height. And so when I do my volume calculation, it's 1 centimeter times 1 centimeter times 1 centimeter. Right? So I multiply my numbers. So in this case, 1 times 1 times 1 is 1. But centimeter times centimeter times centimeter is centimeter cubed. Okay. Now, cubic centimeter is often abbreviated a little differently in the health sciences field. Okay. So instead of writing centimeters cubed like this, it's often written out as CC for the letters that each starts with. So cubic centimeter. Okay. So hearing like 10 cc's or 15 cc's, that's going to be more common than hearing 10 cubic centimeters when you're actually working in, a doctor's office or a hospital or something like that. What a cubic centimeter is also equal to is 1 milliliter. So 1 cubic centimeter and 1 cubic centimeter written as cc, those are the same thing. 1 cubic centimeter is also equal to 1 milliliter. All right. All three of these things are equal in volume. They all mean the same thing. The other equivalency that you need to know, that you have to be comfortable with, is the relationship between liters and milliliters and cubic centimeters, right? So we know that a cubic centimeter and a milliliter are the same thing. That means that if we have 1,000 cubic centimeters, that's going to be equal to 1,000 milliliters. All right. And both of these things are equal to 1 liter. Okay. All right. Let's look at the mass measurement equalities next. Okay, so then the next ones that we want to look at are just some common mass measurement prefixes. Our gram is our base unit, but we know that we give it a prefix in front of that base unit depending on whether we're looking at things that are larger or smaller. When you're measuring, something like something people sized or even pet sized, those units are usually going to be kilograms. Because the mass of people and animals is a little bit larger. Whoops. And so you want to use that kilo prefix to make the number a little more manageable. But when you're working with really small quantities, and a lot of times when you're in labs and you're doing lab work and looking at like lab results, you're going to end up using smaller mass values. And so then you'll see grams or milligrams or even micrograms more often than that. Okay. And then these are just some of the equalities between them, but you can, again, find those on the chart. All right, so let's look at these. Identify the larger unit in each of the following. So between our milli and our centi, we can use the exponents on our table to help us figure out which is the larger value, right? We know that if we have a larger negative number, so if you're comparing like -6 to -3, -3 is going to be the larger value, right? But if we're comparing positive numbers like +6 and +3, then 6 is going to be the larger value. Okay. We'll actually just take the time to write these out, because what I'll do is I'll write the exponent above each of these units so that we can really see which one is bigger and smaller. Oh, they wrote out the word, but it doesn't matter. With kilogram or centigram. I don't think that it matters that I don't write out the word. That's milliliter. And then they use the Scripty microliter. I'm going to write it out like this because, again, I just think that's less confusing. And then kiloliter or microliter. I think they were just trying to make sure that you recognize that these two things, that's the same unit. So with milli and centi, the exponent for milli is 10 to the negative 3. The exponent for centi is 10 to the negative 2. When you're comparing negative exponents, the smaller the number, the larger the value. So our centimeter value is larger. Or, yeah, centimeter. For kilogram or centigram is 10 to the negative 2. Kilogram is 10 to the positive 3. So our kilo is definitely the larger one. Between milli and micro, we're going to have 10 to the negative 3 versus 10 to the negative 6. And so our 10 to the negative 3 value is going to be larger. And then kilo and micro, we're going to have 10 to the positive 3, 10 to the negative 6, and our 10 to the positive 3 is going to be larger here. All right, and so this next section is more focused on writing out the conversion factors. Which is very much linked to those equalities that we were writing down. Okay, so we're going to look at different ways to write equalities and then create conversion factors from those equalities. So an equality is going to be any two things that equal each other. Okay, so they're giving us a lot of different examples down here of relationships between two things. So 1 meter is 1,000 millimeters. That's an equality. 1 pound is 16 ounces. I can write that as an equality. 1 kilogram has 2.20 pounds. That's an equality. And from these equalities, we can build our conversion factors. Conversion factors are going to be when we take our equality and we write it as a fraction. And we're going to have 1 unit on the top and 1 unit on the bottom. And there's always going to be 2 versions of a conversion factor for every equality that we write. So in this case, we can write a version where the 60 minutes is on top and the 1 hour is on the bottom. But we can also write a version of this where the 1 hour is on top and the 60 minutes is on the bottom. Okay, so every equality can create 2 conversion factors. All right, here's another example of that. 1 meter equals 100 centimeters. So our conversion factors can be 100 centimeters on the top, 1 meter on the bottom, or 1 meter on the top, 100 centimeters on the bottom. When you're looking at the metric system or the US system, you'll notice that there's equal signs between the numbers, right? Like when we have like the one, I want to say the wrong number here. 1 pound equals 16 ounces, right? That's a US system conversion. Our 1 meter to 1,000 millimeters, this is a metric conversion. And here, 2.20 pounds equals 1 kilogram. This is when we're trying to equate something from the US system with something from the metric system. Okay. Our list of conversion factors that's in our reference sheet shows us a lot of the common equalities. We have to understand that usually the equalities between our metric and US units are not going to be exact, with one exception. The exception is the relationship between inches and centimeters. This is exact. Inches is our US unit, centimeters is our metric unit. All of the other relationships between the metric and the US units are going to be measured values that will count towards significant figures. Okay? But any equality that is metric, or US to US, those are obtained by definition. So those are going to be considered exact numbers and they will not affect significant figures. Okay. So just to recap, this is a metric conversion. So these would not have significant figures associated with them. 1 pound to 16 ounces. This is a US to US conversion. So this would not have any significant figures associated with it. But our last example here, pounds to kilograms, this is a US to metric conversion. And the measured value, the significant figures part of this, it does not come from the thing that has a 1 in front of it. Whatever has a 1, you don't have to count the significant figures of this part. You do have to count the significant figures of the other value here. So we would say that 2.20, there's 3 significant figures in this number. All right. So this is the same equality sheet that you have from class. And we're going to look at writing out these conversion factors from these equalities. So again, I know there's a lot of repetition here, but it helps us remember when we're writing out metric to metric conversion factors from a metric to metric equality, the values in our equality are considered exact because they're definitions. And so we're not going to be limited by any significant figures here. Okay, these are exact numbers. In this case, with our 1 kilogram to 2.20 pounds, our 1 kilogram will not have significant figures, but our 2.20 pounds will. And these are the 2 versions of the conversion factor that we can use for that. You see, so like one version of the conversion factor, pounds is on top and kilograms is on the bottom. The other version, kilograms is on the top, pounds is on the bottom. So they want us to write out conversion factors from the equalities for each of the following. So let's take a second to do that. And again, I know that I've said this in the other videos too, but every time we get to one of these learning checks, it's a very good idea for you to pause and try it on your own and then compare it to what I end up with. Okay, so that one, meters and inches. And the first thing that you want to do here is you want to go and look on your conversion factor list and find the equalities that relate these things. So that's where I'm going to be getting the first bit of information. I'm going to write out the equality first. And the equalities are going to come from that table that we have from class that has the common equalities listed. So between liters and milliliters, the equality that I would write down is that 1 milliliter equals 10 to the negative 3 liters. Because again, I'm going to put a 1 in front of my prefix, and my exponent is going to go with my base unit. For my meters and my inches, I'm going to look on the table. All right, it says that 1 meter equals 39.4 inches. That is a measured value. That's exact. That one's measured. Okay. In this equality, both of these are metric, so they're both exact. And then down here with meters and kilometers, every 1 kilometer is going to be 10 to the 3 meters. And this is metric, so this is also going to be exact. So now to write the conversion factors from this, I'm going to write one version where my milliliter is on top and my liter is on the bottom. And my second conversion factor is going to have liter on the top and milliliter on the bottom. For my meters and inches, one version I'll have meter on the top, inches on the bottom. And in my second version, I'll have inches on the top and meters on the bottom. And then in my last one, 1 kilometer up top, 10 to the third meters on the bottom, or my meters up top and my kilometers on the bottom. Okay. All right. And so we can also see that we can read a sentence and we can also write conversion factors from the information that we're given within a problem. So here it says the car was traveling at a speed of 85 kilometers per hour. What that means is that for every 1 hour that we travel, we're going 85 kilometers in distance. So the equality that we can make up is that every 1 hour equals 85 kilometers. And then the conversion factors, excuse me, the conversion factors that we would create from that, we'd have one version with our 85 kilometers on the top and our 1 hour on the bottom, and a second version where 1 hour is on the top and 85 kilometers is on the bottom. And the reason that we're creating different conversion factors like this is because depending on the question that we're asked, we'll need either this conversion factor or this conversion factor. Okay. The price of onions is $1.24 per pound. So we can say that every 1 pound of onions equals $1.24. And these are the conversion factors that we can create from it. $1.24 on the top, 1 pound on the bottom, or the opposite. Now keep these conversion factors in mind, and let's just do an example real quick. Let's keep our onion sentence in mind. The price of onions is $1.24 per pound. Okay. And so we write out our equality. 1 pound is $1.24. And we create our conversion factors. Okay. Now let's look at two different questions. So question one is how many pounds of onions can I buy with, let's say, $9.75. And then our second question is going to be how much will 4.5 pounds of onions cost? Okay. So for each of these questions, we're going to use the same equality, but we're going to use different versions of the conversion factors. For our first question, the information that we're given to start with is that we have $9.75 that we're going to be spending on these onions. Okay, so this is our starting information. And when you're writing down, when you're trying to calculate using a conversion factor, the first thing that you need to set up with your conversion factor is your units. So if you start out and you with a number, and in this case, we can consider the dollar as our unit, that means that the dollar has to be on the bottom of your conversion factor so that the dollars can cancel out. So you have to look back at your conversion factor and say, which of these has my dollars on the bottom and my 1 pound on the top, right? And that's going to be the first version that we wrote down there. And if you want to think about it like algebra, then you can think like the dollar signs will cancel out because we have two units that are the same divided by each other, so they'll equal 1. And we'll end up taking 9.75 and dividing it by 1.24. And so we can buy 7.86 pounds of onions with our $9.75. To answer our second question, though, in this case, we're not starting out with a dollar amount. We're starting out with a particular amount of onions that we need. We need 4.5 pounds of onions. How much is that going to cost us? Well, to answer that question, when I set up my conversion factor, now because I'm starting with my unit of pounds, I need to use the version of the conversion factor where pounds is on the bottom so that that unit can cancel out. So now I'm going to use this version of my conversion factor, right? So every 1 pound is going to cost $1.24. So if I want 4.5 pounds, I'm going to need $5.58. Okay. That's why we take the time to write out the conversion factors so that we can plug them into our calculations. Let's look at the next example where we're looking at medicine dosages and how we can write medicine dosages as equalities as well. So here they're telling us that Keflex, an antibiotic used for respiratory and ear infections, is available in 250 milligram capsules. And so with that statement, we can write an equality. And the equality is that for every 1 capsule, it's going to equal 250 milligrams of Keflex. And so when we write out our conversion factors, these are the two versions of that equality. One with the milligrams of Keflex on top. The other version would have the milligrams of Keflex on the bottom. We can do the same thing with percentages as well. And you'll see that percentage, ppm, which is parts per million, and ppb, which is parts per billion, these are all values that are very closely related to each other because all of these calculations start by taking a ratio, like what you have down here. If you have 18% body fat by mass, that means that you have, if you're working in kilograms, you have 18 kilograms of body fat for every 100 kilograms of overall body mass. Okay. That 18 divided by 100, that's a ratio, right? When you have one thing divided by another, that's just going to be a ratio. What turns it into a percentage is when we multiply it by 100. Okay. When you want to turn something into parts per million, instead of multiplying it by 100, you'd multiply it by 1,000,000 or 10 to the 6. If you want to turn something into parts per billion, you'd multiply it by 1,000,000,000 or 10 to the 9. The other way that you can express parts per million or parts per billion is by using your prefixes to help you be 1 million units away from each other. So sometimes when you're in parts per million, you'll see it represented as milligrams per kilogram, because if you count the exponent difference between those values, there's a difference of 10 to the 6 between them, right? Milligram is 10 to the -3, kilogram is 10 to the +3. So that's a difference of 6 in terms of the exponents. Parts per billion is 10 to the 9. Another way you can express this is micrograms per kilogram. This right here, that's a typo because that should be the other unit for micro. This should not be milli. It's microgram per kilogram. The one over here is correct. Um, Microgram is 10 to the negative 6. Kilogram is 10 to the third. So there's, 6 and 3. That's 9. So you could see the difference of 9 there. But as long as there's a difference in terms of your exponents, a difference of 6 for your parts per million and a difference of 9 for your parts per billion, then you're doing it correctly. Let's just look at the ways that we can write that out though. So let's say that we have 18% body fat by mass. When you have a percent, that just means that you're looking out of 100, like your total is 100. So you can use kilograms as your unit to measure your mass. You don't have to use kilograms though. You can write out like they did in the example that what this means is that you have 18 kilograms of fat for every 100 kilograms of body mass. If you were looking at mass in terms of pounds instead, you could say that you'd have 18 pounds of fat in every 100 pounds of body mass. This is also a correct equality for 18% body fat by mass. You just have to make sure that the units that you're using to represent the part and the whole are the same unit. So it's got to be kilograms and kilograms or pounds and pounds. You can't mix and match those when you make your equality. If we were looking at something like the parts per million or the parts per billion, let's say that we wanted to say there was like 18 parts per million. God, I'm trying to think of something that would make sense. I'm totally going to make this up, but just for an example, let's say that there's 18 parts per million of like some pollutant in a body of water. That would be really bad. That would be a pretty big amount. But let's just for an example, okay? So what we would say then is that all right, it's parts per million. So that means that in every let's say there's 18, and you can use different types of units to express this too. We could say that there's 18 grams of pollutant, whatever the pollutant is, in every 10 to the 6, which is a million, grams of water. Okay. If this was parts per billion and we did the same thing, super polluted, well, that one would be more, I guess. 18 parts per billion is a little bit better. But I just want to write out the equalities so you can see them. If we were doing 18 parts per billion, you could write that there's 18, I'll switch it up here, kilograms of pollutant in every 10 to the 9 kilograms of water. Right? But you see like these, it's just that these units have to match internally. All right. And the value that goes along with ppb or the value that goes along with ppm, that represents the part that you're looking at. And the 10 to the 9 or the 10 to the 6 or the 100, that represents the whole amount. Okay. All right, so let's look at the next example here. All right, so this asks us to write the equality and its corresponding conversion factor, identify the number as exact or give its significant figures in the following statement. And it just says salmon contains 1.9% omega-3 fatty acids. Okay. From that information, you can write down an equality saying that, let's say you have 100 grams of salmon, and you know that your total is going to be 100 because you're using a percentage, and percent is always out of 100. So in 100 grams of salmon, 1.9 of those grams is going to be your omega-3 fatty acids. Okay. In these values, the 100 grams, this is exact because that's the definition of a percent. And the 1.9, this is measured. So this would have significant figures associated with it. And then the two conversion factors that we could build from this equality. Remember, this is going to be our equality. And for our conversion factors, we can write that that in 100 grams of salmon, there's 1.9 grams of omega-3, or we can write that there's 1.9 grams of omega-3 in 100 grams of salmon. All right. Let's look at the next one. More examples up here. So for each of these, it wants us to write the equality and the conversion factors for each thing that's given here. And again, this is a really good one to pause at this point and try this on your own. And then you can watch the solution. All right, so we'd start for each of these by writing out the equality, our relationship between centimeters and meters. Every 1 centimeter is going to be 10 to the negative 2 meters. That's our equality. And then we can build our conversion factors from that. So we'll do 1 centimeter over 10 to the negative 2 meters, or 10 to the negative 2 meters for every 1 centimeter. Jewelry that's 18% gold. So if it's 18% gold, that means that if you have 100 grams of jewelry total, like say that your total mass for your jewelry is 100 grams, 18 of those grams is going to be gold. All right. And then the conversion factors that you can build. 100 grams of jewelry will have 18 grams of gold, or there's 18 grams of gold for every 100 grams of jewelry. And then the last one, 1 gallon of gas is $3 and $3.40. So our equality is going to be that 1 gallon equals $3.40. And then these would be our corresponding conversion factors. All right. So the next section is actually using these conversion factors and solving problems with them, which is probably where we'd want to spend the most time anyway. So let's look at the intro stuff and then we'll get to those examples. So just in general, the process of problem solving in chemistry often requires one or more conversion factors to change a given unit, which is what we start with, to the needed unit, which is what we want to end with. So when you were trying to solve a problem, we need to identify the given quantity units, which is the units that we're starting with. We're going to need to look at the units that are needed, which is the units we want to end with. And we need to identify the conversion factors that are going to link those different units. Okay. It's like making a roadmap for yourself. Okay. So like in this question, it says if a person weighs 164 pounds, what's the body mass in kilograms? Well, your given unit is the pounds, right? You're told that that the person weighs 164 pounds. So this is going to be your given unit. And the needed unit is going to be kilograms. And so then you have to connect pounds and kilograms using the correct conversion factor. Okay. All right. So we're going to do most of these. We'll just do these examples, the next few examples on the board. So if a person weighs 164 pounds, what is the body mass in kilograms? Okay. So our goal is to go from pounds into kilograms. And so we want to look up the conversion factor that allows us to do that. You can look back at the table that we were using before. We've also used this conversion factor in some of the other examples. But our conversion factor that we need here is that for every 2.20 pounds, there's 1 kilogram. And now we're going to look back at our question and we're going to start with the number that's given to us in the question. And we want to make sure to write down the unit as well. Because this unit is going to tell us which version of our conversion factor from this equality that we would need to use. Okay. If we're starting out with pounds, that means that in our conversion factor, pounds needs to be on the bottom so that these can cancel out. And that means that kilograms has to be up top. Right. And so 2.20 goes with our pounds, 1 goes with our kilogram. And so we're going to do 164 divided by 2.20. And we end up with 74.5 kilograms. All right. The next question says that a rattlesnake is 2.44 meters long. How many centimeters long is the snake? Okay. And so our map that we can make for ourselves is we're trying to go from meters into centimeters. And so we want to write down our conversion. Every 1 centimeter is going to be equal to 10 to the negative 2 meters. And then we can set up our problem. The information that we're given here, 2.44 meters. And so when we set up our conversion factor, we know that we're going to want meters, the unit of meters on the bottom, the unit of centimeters up top. 10 to the negative 2 goes with our meters. 1 goes with our centimeter. Our meters units can cancel out then. And we get 244 centimeters. Okay. Okay. And for our next one, they give us, they say Levsin used to treat stomach and bladder problems is available as drops with 0.125 milligrams of Levsin per 1 milliliter of solution. The second statement they give us is the EPA has set the maximum level of cadmium in rice at 0.4 parts per million. And so for this particular question, the overall question was write the equality and the corresponding conversion factors and identify each number as exact or measured, and then the significant figures if it's measured. So we're not doing the full calculation from this one. For this question, they ask us to like backtrack a second and look at the equalities again. So with these statements for part A, with our 0.125 milligrams of Levsin per 1 milliliter of solution, our equality is going to look like this. 0.125 milligrams equals 1 milliliter of solution. And then our corresponding conversion factors would be 1.125 milligrams over 1 milliliter, or 1 milliliter is 0.125 milligrams. In this equality, our 1 milliliter is exact and our 0.125 is measured. And there's 3 sig figs there. Okay. For our next statement, the max level of cadmium in rice is 0.4 parts per million. That means that we can have, again, there's a few ways to write this. One of them going right by the definition of parts per million is that you can have 0.4 grams of cadmium, CD, in every 1 million grams of rice. But you can also write this as 0.4 milligrams of cadmium in every kilogram of rice. These equal the same thing. They mean the same thing because there's a 6 exponent difference between them in both cases. For this one, when we write out our conversion factor, then this is version 1. And this is version 2. in this conversion factor, our 10 to the 6 and our 1 kilogram, both of these are exact values. Our 0.4 is our measured value, and there's only one significant figure in that value. All right. So I'm going to put up the next question because I'm not going to write the whole thing out, but what I am going to write out while this question is up on the screen, I'm going to write out the equality that we can get from the question, because we're going to use that equality to solve the problem. Okay, so here they're telling us that we have a doctor's order prescribed a dosage of 0.150 milligrams of Synthroid. So the doctor's ordering 0.150 milligrams of the Synthroid. And they're telling us that every tablet contains 75 micrograms of Synthroid. That is our equality. Every tablet contains 75 micrograms, mcg. So one tablet equals 75 micrograms. Okay. And then the question is, how many tablets are we going to need to provide the prescribed medication? Okay. So how many tablets do we need? What you've got to be careful of when you're solving these questions is a case like this one, where one of our values is given to us in milligrams, which is mg, and the other mass value that we're given is in micrograms, mcg. We're not going to be able to use our equality until the unit that we have here matches the unit that we have here. Okay, so we have to make that connection. We have to make that pathway for ourselves. We have to take our milligram value and we have to convert it into micrograms. And once our number is in terms of micrograms, then we can figure out how many tablets that we need. Each of these arrows represents a step that we have to take. So our first step is going to be to take our milligrams and turn it into micrograms. And we need an equality for that, or a series of equalities if we don't know just one equality. And unless you're very familiar with prefixes, you might not know the conversion between milligrams and micrograms directly. Okay, and that's fine. Anytime that you're trying to convert one prefix value into another prefix value, you can always do that by using your base unit. In this case, our base unit is grams. So what I mean is, we can take our milligrams and we can turn that into grams using our table and our prefixes that we already know. And then we can take our value that's in grams and we can turn it into micrograms. Okay, so our conversion that connects these two values, every 1 milligram is 10 to the negative 3 grams. And then to connect these two units, every 1 microgram is 10 to the negative 6 grams. Okay, so if I have 0.150 milligrams, I can use my conversion factor that has milligrams in it, and I can turn it into grams. So I'm going to put my 1 milligram on the bottom so that my milligram units can cancel out. And my 10 to the -3 grams up top. You can make one long conversion factor to do these calculations, or you can break it up in steps if you're struggling with this. Okay. So if I put this in my calculator, I'm going to get 1.5. It says 3 sig figs, so we'll keep 3 sig figs here. 1.50 times 10, the -4 grams. Okay. And then we're going to take our grams and we're going to turn it into micrograms. So our grams unit is going to go on the bottom and our micrograms unit is going to go up top. So 1 microgram, 10 to the -6 grams. Well, I should really write that the other way because we're going from grams into micrograms. But now we see our grams unit cancels out. Okay, and we end up with 1.50 times 10 to the 2 micrograms. Now that we know how many micrograms we have, now we can use our equality that relates our micrograms to our numbers of tablets. So if we have 1.50 times 10 to the 2 micrograms, we know that we're going to want to put our microgram value on the bottom so that the micrograms cancel out. And we're going to want to put our tablet up top. And we see that there's 75 micrograms per tablet. Okay, so now our microgram unit cancels out. 150 divided by 75. And we get 2 tablets. That's how many we would need. All right, next question. How many minutes are in 1.4 days? Okay, so we want to go from days into minutes. That's our given unit. This is the unit that we need. But we are likely not going to do this in one step unless you know that conversion off the top of your head. We're going to have to go from days into hours and then from hours into minutes. And so our equalities are going to be that for every 1 day, there's 24 hours. And then for hours and minutes, every 1 hour is 60 minutes. And these are all exact numbers because they're all definitions. So if I have 1.4 days, then my first conversion, I'm going to have my days on the bottom and my hours up top. So every 1 day, 24 hours. And then in my next step, I can put my hour on the bottom and my 60 minutes up top. And my hours unit cancels, and I'm going to be left with my unit in minutes. 1.4 times 24 times 60. And I'm going to end up with 2016 minutes, but I'm going to round that to 2 significant figures because there's 2 significant figures in 1.4. So that's going to be 2.0. Well, I'll write it all out first. So we get, and then we're going to keep these 2. So that rounded, that's 2,000 minutes. But we can't leave it like that because that implies that there's only one significant figure and we're significant up to that 0. So we're going to rewrite that as 2.0 times 10 to the positive 3 minutes. Okay. Next question. If your pace on a treadmill is 65 meters per minute, how many minutes will it take for you to walk a distance of 7.5 kilometers? Okay. So here they are giving us kilometers to start with. That's our given unit. And we need to convert that into minutes. Okay. The conversion factor that they gave us here is this one, saying that we can go 65 meters in every 1 minute. Or I should say that's the equality that they gave us that we can turn into a conversion factor. So that's good. We have a unit of minute here. We have the unit of minute here. Those match. That's good. But we have meters here and we have kilometers here. So that's a mismatch. So we have to make these things match before we can use our conversion factor. So our first step here is going to be to take our kilometer value and we're going to turn that kilometer value into meters. And then once we do that, we can use our conversion factor and we can convert our meters into minutes. Okay. So our equality that relates kilometers and meters, every 1 kilometer, 10 to the 3 meters. So we take our starting amount, 7.5 kilometers, write out the whole thing, including the units. And in our first conversion factor, we're going to use the equality that has our kilometers and our meters in it. So our 1 kilometer is going to go on the bottom so that our kilometer unit can cancel. 10 to the 3 meters up top. And again, you can write this out in one long thing, or you can go through and write it out separately if you're just not feeling super comfortable with this yet. Okay, but we have 7,500 meters. Once you have your value in meters, then you can use your second equality and go from meters to minutes. I'm just going to write the word meter out so that it doesn't get. So our equality tells us that we can go 65 meters in every 1 minute. Okay. Meters are on opposite sides of the fraction bar so that we can cancel. And we end up with 115.38 minutes. We would want to round this to 2 significant figures because 7.5 and 65 both have 2 significant figures in them. So our final answer should have 2 significant figures. So this will be 120 minutes if we're being correct with our significant figures. All right. Next question. On to Greg and all of his problems. Greg's doctor has ordered a PET scan of his heart. In radiological imaging, dosage of pharmaceuticals are based on body mass. So if Greg weighs 257 pounds, what is his body mass in kilograms? Okay, so here our given information is pounds. Our end information is going to be kilograms. And we want to use the equality that relates those two things, which is going to be every 2.20 pounds equals 1 kilogram. And then we can set up our calculation starting with our given value. So 257 pounds. And when we set up our conversion factor, we're going to put our pounds value on the bottom so that our units cancel. And we'll put our 1 kilogram up top. And that's going to be 117 kilograms. Next question. Greg has been diagnosed with diminished thyroid function. His doctor prescribes a dosage of 0.225 milligrams of Synthroid. Okay, 0.225. Okay, looks too small. To be taken once a day. 0.225 milligrams to be taken once a day. If the tablets in stock, again, contain 75 micrograms per tablet, how many tablets does he need to take every day? Okay, so we talked through some of this before. We're starting out with a value that's in milligrams. And in our conversion factor, which is going to be 75 micrograms for every 1 tablet, our conversion factor has a mass that's in micrograms and not milligrams. So our first step is going to be to take our 0.225 milligrams and turn it into micrograms, right? The conversion factors that we'll need for that, every 1 milligram is 10 to the negative 3 grams. Every 1 microgram is 10 to the negative 6 grams. Okay, so I'm going to start with my milligrams and convert that into grams. And this time we'll build it in one chain. Okay, so now my next step, I'm going to take my grams and I'm going to convert it into micrograms. Sorry, that should have been 10 to the negative 3. Okay, 1 milligram is 10 to the negative 3 grams. And then my next step with my micrograms, there's 10 to the negative 6 grams in every 1 microgram. And then in my last step, I can use my equality that includes my tablets. So there's going to be 75 micrograms in every 1 tablet of the medication. Now my microgram unit cancels out as well, and I'm just left with my tablets. And he'll need to take 3 tablets every day for his thyroid. All right. Our next 2 questions are going to use mass percent in them. So for this one, the information that we're given is that we have 1.33 pounds of meat, and that the meat is 15% fat by mass. So 15% fat. They're also asking for the final value to be given to us, to be given in terms of grams. They want to know how many grams of fat are in this ground round. Okay. What that means is we're going to have to take our value that's in pounds, and we're going to have to convert it into grams. So we can say we have however many pounds of like meat total. We're going to turn that into grams of meat. Okay. And once we know how many grams of meat we have, then we can use our percentage to figure out how many grams of fat there are. Okay. To do our conversion between pounds and grams, go back to your conversion table and take a look in the mass section. The conversion for that is mass. 454 grams in every 1 pound. Okay. And then for our percentage, when we take this 15% fat, we can write that in terms of grams since we want our final answer in grams. So this is going to say there's going to be 15 grams of fat in every 100 grams of meat. That's what our percentage tells us. Okay. So start out up here. If we have 1.33 pounds of meat in our first conversion, we're going to take our 1 pound, put it on the bottom, and our 454 grams up top. You can do this in 1 step or 2 steps. Either is fine. I like to switch it up just so you could see both methods. So this is going to be 603.82 grams. For now, we're keeping 3 significant figures, although that's going to change when we introduce this part. And this is the grams of our meat, total package of ground round that we have. Now to figure out our percent fat from that, now we're going to be incorporating this equality here. So this represents our total amount of meat. So now we're going to, on the bottom of our conversion factor, we have to use the value that represents the total amount of meat. That's going to be the 100 grams. So now that unit can cancel out. And what goes up top is going to be our 15 grams of fat. And we end up with 90.573 grams, which we're going to round to two significant figures. So that 5 will round the 0 up to a 1. And we'll have 91 grams of fat in that package of round. All right, and let's look at question B from that same section. A cream contains 4% by mass lidocaine. To relieve back pain. If a patient uses 12 grams of cream, how many milligrams of lidocaine are used? Okay, so from our percentage here, we're going to be able to relate the amount of lidocaine that's in the total sample of cream. What 4% tells us is that if we had 100 grams of cream total, that 4 of those grams would be lidocaine. Okay, that's what our percent tells us. So if we have 12 grams of cream, then we can use that equality to figure out how much lidocaine is in 12 grams of cream. If I only have 12 grams of cream, then I can say, all right, well, 100 grams of cream is going to have 4 grams of lidocaine. And I can use this relationship or this proportion to figure out how much lidocaine is going to be in my 12 grams. Okay. Now this question asked us to figure out how many milligrams of lidocaine are used, and the answer we get here is in terms of grams. So we do want to make sure that we go one step further and convert our grams into milligrams. And so our second equality that we're going to want to look at will be between milligrams and grams. So we have a gram value up here. So we're going to put our gram unit on the bottom so that it cancels, and our 1 milligram up top. And we're going to end up with 480 milligrams of lidocaine. Okay. All right, let's look at the LD50 next. The last thing that we have to look at before we transition into the density section is a link specifically to like toxicology and lab work that you'd look at. And one way to measure toxicity is by the lethal dose, okay? The LD50 value. This is the value that represents the concentration of the particular substance that you're working with that would cause death in 50% of the test animals, okay? A lot of times pharmaceuticals, when they're deciding whether something is safe or not, they do test on animals. And so to figure out the toxicity level of different things, they use the LD50 value as a gauge of how dangerous something is. Just as an example, if you're looking at something like caffeine, the LD50 is 192 milligrams for every kilogram of body mass. And then you can look in your textbook if you want to see some particular examples of LD50 values. You don't have to know individual numbers, but you do have to know what the LD50 means and what it's used for. Okay. So let's look at density. Density is an intrinsic property of substances. It can help us identify substances. And when we want to calculate density, we want to use the density equation, which is density equals the mass of a substance divided by the volume of that substance. We can use the relative density of objects to kind of figure out their information. You can see what's happening in this situation here. You've got a whole bunch of stuff in a beaker of water, and what's interesting about density and like how density is related to like density of one thing is related to the other thing is that you can see here that some things float and some things sink. All of these things are in relation to liquid water. So things that are floating are things that are less dense than liquid water. So like the cork is less dense. The ice cube is less dense because solid water is less dense than liquid water. But the things like aluminum and lead are more dense, so they're going to sink to the bottom. The lead is the most dense out of all of these things. But we want to be able to calculate density values of different things. We want to be able to use density to do other calculations as well. Some typical density units are grams per cubic centimeter or grams per milliliter. That's the standard units that you would use for density if you're working with solids and liquids. When you're working with the density of gases, it's more common to use grams per liter as your unit. And when you want to find the density of a solid, that's not always an easy task because finding the volume of certain solids is difficult. If you were going to use a traditional like length measuring system. But what you can do to find the volume of sort of odd shaped solids in particular is you can use water to help you out. Right. So you can take a certain amount of water, in this case, in a graduated cylinder, and you can get the measurement of that water when the graduated cylinder has no metal substance in it. And then you can take your piece of metal and you can put it inside the graduated cylinder. And when you do that, the metal is going to take up space here, right? And so as the metal takes up space, it's going to push the water level up. Okay. And so now you're going to take this new reading, this new volume reading. And to figure out the volume of the metal that you put into the graduated cylinder, you'll take that new larger volume and you'll subtract the original volume from it. And the difference in these two things is going to represent the volume of your piece of metal. Once you do that, you can figure out what the density is, because density is just going to be the mass of the object, which you can get from your balance, divided by the volume of the object, which you get from this subtraction. Then that will tell you the density. Okay, so here they took the 45 milliliters, which was the density of the water in the graduated cylinder plus the zinc metal. And they subtracted it from the volume of the water by itself, giving us a volume of 9.5 milliliters for the solid cylinder piece. And then to find the density of that zinc, take the mass value, which is a 68.60 grams from your balance, divide it by the volume of the zinc, of the zinc, which is 9.5 milliliters or centimeters cubed. And when we divide those, we get 7.2 grams per cubic centimeter. So let's take a look at this question. It says, what is the density in grams per cubic centimeter of a 48-gram sample of metal if the water level in a graduated cylinder rises from 25 milliliters to 33 milliliters after the metal is added? So we'll have an initial volume. We're going to have a final volume. We're going to subtract those to figure out what the volume of the metal piece was. So the 33 milliliters is going to represent the metal sample plus the water. And now to find the density. Oh, well, I got to stop so you can see my screen. So our initial volume was 25. Our final volume was 33. Volume of the metal is going to be the 33 minus the 25, so 8 milliliters total. And to find our density, we'll take the mass value, which they told us was 48 grams, divided by the volume of the metal, which is our 8 milliliters. And then our density is going to be 6 grams per milliliter or 6 grams per cubic centimeter. Okay. Next example says John took 2 teaspoons of cough syrup. If the syrup had a density of, I'm just going to use that for density. So density is 1.20 grams per milliliter. And there is 5 milliliters in 1 teaspoon. What mass in grams is the cough syrup that he took? Okay, so we have 2 different equalities that we can work with here. Equality 1, which tells us which is our density. When you're given a value like density, where you have 1.20 grams per, like, then divided by milliliters, what that means is that for every 1 milliliter of that substance, there's a mass of 1.20 grams. So you can take that density and you can rewrite it as an equality. Because what that density is telling you is that 1.20 grams of cough syrup is going to have a volume of 1 milliliter. Okay. And the second equality that they tell us is this one, that for every 1 teaspoon of this cough syrup, it's going to be 5 milliliters. Right? So what John took was 2 teaspoons, right? He took 2 teaspoons. Well, we know that every teaspoon is going to be 5 milliliters. Okay, so we know that there's 10 milliliters that he took. And then we also know that every 1 milliliter is going to have a mass of 1.20 grams. So the mass of the cough syrup that he took is going to be 12 grams. Okay, and we're going to keep that to two significant figures based on the calculations from over here. We had two sig figs from that number. Right, our next question says an unknown liquid has a density of 1.32 grams per milliliter. What's the volume in milliliters of a 14.7 gram sample of the liquid? Okay. You can do this two ways. You can solve the density equation out, and you can, plug in density equals mass over volume and solve it for volume. You can also use density like a conversion factor and write out for yourself the equality that for every 1.32 grams of this liquid, it's going to occupy 1 milliliter of space. So if you have 14.7 grams in your sample, you know that every 1.32 grams is going to be 1 milliliter of space. Which gives you a final volume of 11 milliliters. The other way you can look at this question is by taking your density equation. Okay. And you can say, all right, well, I have a density and I have a mass. I'm going to solve it for volume. So to solve it for volume, I'm going to multiply both sides by volume. And then I'm going to divide both sides by density so I can get the volume all by itself. And I'm going to have my mass divided by my density, which if you'll notice is the same calculation we did here. So our mass is going to be 14.7 grams. Our density is 1.32 grams per milliliter. Just putting this back in to make sure that I did it right the first time. And so when we do that back out, we still end up with 11 milliliters. It should be the same, right? Both of those methods, you do the same thing. It's just one of them, you might think about them a little differently, one versus the other. All right, the last topic that we want to look at, I'm going to bring the slides back up. Before we do our last round of examples is specific gravity. Specific gravity looks at the relationship between the density of any substance as it compares to the density of water. And you're going to calculate the specific gravity by taking the density of your sample and dividing it by the density of water. Specific gravity is a unitless quantity because when you calculate specific gravity, your units will end up canceling out in this calculation. And so you see the setup over here to calculate the specific gravity of something. You'll take the density of that substance, you'll divide it by the density of water. Okay. And then you'll get your specific gravity. All right. Just going to look at the last set of examples here. I'm going to pause real quick while I write this down. Okay, so let's stop sharing and solve these out. Both of these examples just want us to calculate the density flat out. So we're not going to be really manipulating the density equation. We're just going to be using it. So for our first one, density is mass over volume. Our mass is going to be 0.380 milligrams. Our volume is going to be 0.362 milliliters. You have to pay attention to the units that you're given and the units they ask about in the question. This question specifically asks, if you look in your notes, for the mass to be reported in units of grams, which is usual for a solid or a liquid, and the volume to be reported in milliliters. And that means that you have to take your milligram mass and you have to convert it into grams before you can use your density equation. Okay. So if I want to go from milligrams to grams, I want to set up my equality for that first. Every 1 milligram is going to be 10 to the negative 3 grams. So if I have 0.380 milligrams, 1 milligram, just put this in here so I don't confuse the decimal movement. Once you have the value in grams, it actually should be the 3 significant figures still because this has 3 significant figures. So once we have our value in grams, our volume is already in milliliters. So now we can plug this in directly. So we're going to have 3.80 times 10 to the negative 4 grams divided by 0.362 milliliters. And we end up with 1.05 times 10 to the negative 3 grams per milliliter. Second question, if a bone sample has a mass of 2.15 grams and a volume of 1.40 cubic centimeters, what is its density? And they want grams per cubic centimeter as the units for this one. Okay, so mass in grams over volume in cubic centimeters. Okay, and so we'll do 2.15 grams over 1.40 cubic centimeters. We end up with 1.54 grams per cubic centimeter. All right. Next question. Back to Greg. Let me put it up on the screen. So for this one, we're going to need to take Greg's blood volume in quarts, and we're going to have to relate it back to milliliters so that we could figure out the grams. Okay. So if you don't have all of your conversions, memorized yet, you got to pull out the conversion sheet for this one. Let's see what they give you for volume conversions. You get quarts and liters. Okay. So they give us the conversions. I'm using the ones from the table because I want to use the ones that you're going to be more familiar with. So when you're looking at the metric US conversions that are on your table, the volume conversion that they give us that to link the two of them is that every 1.06 quarts equals 1 liter. From there, split this apart. We can connect liters to milliliters using our metric conversions. Every 1 milliliter is going to be 10 to the negative 3 liters. Okay. And then again, remember that we can take density and we can write that as an equality as well. So what the density tells us is that every 1.06 grams of blood takes up a volume of 1 milliliter. Okay. So if Greg has a blood volume of 5.9 quarts, we can take the quarts, we could turn it into liters. Then we can take the liters and turn it into milliliters. Then we can take those milliliters and we can turn it into grams. Okay. And that's going to be our plan of action here. So we're going to start by rewriting the 5.9 quarts. And this is going to be our first conversion, taking the 5.9 quarts and turning it into liters. Okay, and you can do this in 3 steps or you can do it all in one chain. I'll do the next one in one chain. I'll do this one in the steps. Okay, and we watch the quart units cancel out. And that tells us we have 5.5. I'm going to keep extra digits here, even though we're only going to end with 2 significant figures. I'm going to just keep more digits until the very end, but I'll keep track of my significant ones. So this is how many liters we have. And then we'll turn our liters into milliliters. So there's going to be 10 to the negative 3 liters in every 1 milliliter, which means we're going to end up with 5,566 milliliters. And you see our liters unit cancels out. And then with our last conversion, we'll go from milliliters into grams. Every 1 milliliter is going to be 1.06 grams. Okay. We're still keeping 2 significant figures there. I'm checking off only 2 significant figures for these because I'm going back to the 2 significant figures that were in 5.9. So over here, when we get 5,900 back out, it works out nicely that happened because we need to keep 2 significant figures. So we can write it out as 5,900, or we can write it out as 5.9 times 10 to the 3 grams. Either of these answers would be perfectly fine. Okay. Next question. Again, let me share the screen so that you guys can see the questions as I write them. Okay. There we go. Okay. So last two questions for this section. First one is a patient receives 3 pints of blood. How many kilograms of blood were needed for the transfusion? And we're going to use the density to help us out with that. So the density is the first equality that they give us. So we know that there's going to be 1.06 grams of blood in every 1 milliliter. The other conversion factors that we're going to need, we're going to need to take pints and we're going to need to relate it to milliliters. So we have to look back at our list of conversion factors to see how we can do that. One way that I see from the list of conversions that you have is that you have the 473 milliliters equals 1 pint conversion. And this is just from the table. So 473 milliliters equals 1 pint. And then the last conversion that we're going to need, we need to have our answer in terms of kilograms. So we're going to need to be converting grams into kilograms. 1 kilogram equals 10 to the 3 grams. So those are the 3 equalities that we're going to need. We start out with our 3 pints of blood. Okay, so we'll build one long conversion factor for this one. So if we have 3 pints of blood, the first conversion that we're going to make is to take our pints and convert it into milliliters. That's how you know where to start. Because if they start with pints, you start with pints. If they started with quarts in the last example, so we started with quarts. So we'll put our 1 pint on the bottom and our 473 milliliters up top. Okay. Now in our next step, if you're looking at what's left, which of the equalities you need to work with next, we have milliliters up here in our numerator spot. So the next conversion factor you need to build needs to have milliliters in it. And we'll go from milliliters into grams. Okay. So our 1 milliliter will go on the bottom and our 1.06 grams of blood will go up top. And now in our last step, we're going to go from grams into kilograms. So the 10 to the 3rd grams goes on the bottom so that our grams cancel out. Our 1 kilogram goes up top. And we end up with, we're going to keep 2 significant figures here. So 1.5 kilograms of blood. Okay. Last example here, a woman receives 1,280 grams of blood type A. If the blood has a density of 1.06 grams per milliliter, how many liters of blood did she receive? So we're going to take our grams of blood and we're going to convert it into milliliters first using our density. Then from milliliters, we'll convert it into liters. Okay. So for this first step, we're going to use our density. And for this second step, we're going to use our metric conversions. Okay, and the equalities that we get from this example, first one is 1.06 grams of blood. No, we're rewriting this a lot, is 1 milliliter. And then to do our metric conversion, every 1 milliliter is going to be 10 to the negative 3 liters. So these are our 2 equalities that we're going to need to build our conversion factors. So we'll start out with our mass that we were given, 1280 grams. And in our first step, we're going to use our density to go from grams to milliliters. We'll do this one in pieces since we did the other one in one step. Uh, 1280 divided by 1.06. Okay, we get 1207.55 milliliters. And I'm going to note to myself that 3 of my digits are significant because this number has 3 significant figures and this number has 3 significant figures. So even though I'm keeping more digits in my calculator, this number still only has 3 significant figures in it. And now I'm going to convert it from milliliters into liters. So every 1 milliliter has 10 to the negative 3 liters. And we end up with 1.2075 liters. We want to keep 3 significant figures. So that 7 is going to round the 0 up to a 1. We end up with 1.21 liters. Okay. And that's the last example from chapter 2.